Again. Today I guess I'm going to talk a little bit about Seifert fibered spaces. So this is chapter 3. So remember we're sort of focusing on this conjecture that if you have a prime 3 manifold, then it's LO, which is shorthand for its fundamental group being left orderable. If and only if it is not an L space. Adam was talking about that today. And the third condition is that M has a co-orientable taut foliation. And so we'll abbreviate this, we'll just say M is CTF. And as I mentioned before, the only implication here that's known sort of unconditionally is that the CTF implies NLS, and that's Osvat-Szabo plus Kazes, Roberts, and Bowden to remove the sort of smoothness assumption on the foliation. Well, so I mean, maybe I should. I mean, what's the background to this? I mean, first of all, when Osvat and Szabo proved this implication, they sort of raised the question. I can't remember whether they directly said, you know, is this a topological characterization of L spaces? But at least they asked, is there a topological characterization of L spaces? So the implication clearly was that this might be. This was actually explicitly conjectured, I think, by Andras Juhas. I think he was perhaps the first person to explicitly conjecture this. And again, the connection between left orderability and co-orientable taut foliations, again, that was sort of well established, going back to the work of Roberts and Sureshian and Stein, and then the connection, therefore, with L spaces got work with, well, Boyer and Peters. So a lot of these things were in the air, and so this equivalence was explicitly conjectured by Steve Boyer and myself and Liam in a paper. And so, but these ideas were all sort of in the air. But by the way, I'm a big believer in making conjectures, you know, because it appeals to people's competitive nature, you know. If you ask a question, well, you know, hey, you know, if you answer a question, who cares? But if you disprove somebody's conjecture, that's really. On the other hand, I remember many years ago, I was reading a math review. This is before Math Scinet, okay, math review. And the review was, in this paper, the author gives a counterexample to a question of Gordon. So. You can't win. Anyway. All right, Seifert fibered spaces. Of course, many of you know this, but let's... So, a Seifert fibered space, which I'll abbreviate, of course, to SFS, is going to be, for the moment, let's... Ultimately, we'll be interested in closed manifolds, as usual, but for the moment, because I want to say a little bit of the background here, for the moment, let's just say this is a compact, again, connected orientable, but a compact 3 manifold M that is the union, that is a disjoint union of circles, which I'll refer to as fibers or Seifert fibers. It's not, they're not fibers in the strict sense of vibration, but Seifert fibers such that each fiber has a neighborhood, which is equal to a union of fibers. So it's and it's actually isomorphic, you know, as a fibered object to a standard gadget, namely what one might call a fibered solid torus. So that's going to be a solid torus with a with an obvious sort of structure of this type. Namely, let's just take, so we take a cylinder D2 across the unit interval, and now just let's identify the two ends by rotation through an angle, let's say 2 pi q over p, where p is some integer greater than or equal to 1, and q is relatively prime to p. And of course, now this then induces a sort of fibered structure in the solid torus. You get one central fiber, and then you get, if p is greater than 1, you get a bunch of fibers that wrap p times round longitudinally. And one says that the central fiber, so if p is greater than 1, then this central fiber is said to be exceptional of multiplicity p. Okay, so that's okay. I won't say any more. That's just the definition of a Sachet fiber space. You could easily see that S3, for example, is a Sachet fiber space. Okay. Now these things. Oh yes. So let's just notice that if the boundary is non-empty, well, so you should think of this as a. I mean, it's almost a circle bundle over a surface, but there are a finite number of sort of exceptional fibers corresponding to the finite number of central fibers of this type. But the boundary, nothing interesting is going to go on the boundary. So the boundary of such a thing is going to be a disjoint union of tori. Of course, possibly empty. I mean, I'm allowing the case where M is closed. Okay. So it turns out that these spaces, well, they were studied by Seifert in the 1930s, and I'll explain why he was led to look at these things in a little while, but he just gave a complete discussion of those things, a complete theory in a beautiful paper, nothing more to be said. And in fact, nothing more was said until several decades later. But it turns out that they are these are the sort of, one of the basic building blocks of free manifolds. So let me just briefly mention that. Again, this is familiar to most of you, I'm sure. But so now let's suppose M is a closed free manifold, and let's say that so if we have a torus T in M, we say it's incompressible. I mean, this is not really the definition, but this is equivalent to the definition. It's incompressible, so it's as easy to say this. It's incompressible if the inclusion map on pi 1 is injective. Okay, so that's the notion of an incompressible torus. And again, the geometrization conjecture. So let me just very briefly state that. This will be probably relevant to some of the later talks. So I want to get in. So suppose you have a prime, remember, closed prime three manifold. So it turns out that I mentioned the Knaser-Milnor theorem. So there's this canonical decomposition of an arbitrary manifold into a connection of prime manifolds. There's a further decomposition along incompressible tori, and so. In fact, so there exists a canonical disjoint union of incompressible tori. Let's call it script T in M, such that for each component N of M cut along T. So you cut this, cut the manifold along these tori. If each component N, either N is a Seifert fibered space, or the interior of N has a complete hyperbolic structure. So that's a quick, and of course, so let me say that in the case when this collection of tori is non-empty, I mean, this was all done classically. This collection, I mean, this decomposition is known as the JSJ decomposition, as most of you know. This was Jaco, Shalen, Johansson. The fact that the pieces that were not Seifert fibered, they were called simple, and then Thurston showed that in fact they are hyperbolic. So of course this is and in the case where there are no tori, well, again, many cases of this were known. In fact, again, as most of you know, in the case where M contains some incompressible surface, this was known. But in total generality, this wasn't proved until Perlman. And so, in particular, then. If pi 1 of m is finite, then it clearly doesn't contain any incompressible tori, right? Because pi 1 of t is z cross z, and so it must be either Seifert fibered or it has a complete hyperbolic structure. Well, it can't have a complete hyperbolic structure because then pi would be infinite again. And so if pi 1 of m is finite, then M is a Seifert fibered space. And so and we've already seen some examples of those. We've seen lens spaces. We saw the sigma 235 today. In fact, this is actually this is the origin of the study of Seifert fiber spaces. You see, Seifert and somebody, maybe Seifert and Trelfall, and Hopf as well was involved in this. If you look at the subgroups of SO4 that act freely, the finite subgroups of SO4 that act freely on the 3 sphere, you could classify, and so these were, these were the only known 3 manifolds with finite fundamental group, and of course now we know that they are the only ones, but they were classified a long time ago, and Seifert noticed that these groups, the action, the action of this finite subgroup SO4, it always commutes with the Hopf action, the circle action on S3 that comes from the Hopf vibration, and so that descends then to a structure on the manifold with finite fundamental group, a structure as a Seifert fiber space, and so Seifert noticed that and said, hey, well, why don't we just study manifolds that have this kind of structure in general, not just the ones with finite fundamental group, and which he did. Like I said, he completely. It's a beautiful paper. I highly recommend it. It's just, he starts from the definition, and he ends up 100 pages later with a complete theory of these objects. Okay, so so from the point of view of closed manifolds, then, if we're looking at this maybe conjecture, one might think, well, the simplest class of examples would be the Seifert fibered spaces, and I mean the closed Seifert fibered spaces. So that's what I'll talk about today. By the way, again, and this will probably, I'm sure Liam will be saying more about this. The next. In terms of complexity, the next class of closed 3 manifolds you might look at from this point of view then would be those that do contain incompressible tori, but such that all the pieces, all these ends, are Seifert fibered. And so these are the so-called graph manifolds. And so that would be the next class of manifolds that people might look at, and indeed that's what happened. That leaves, of course, in particular it leaves the closed hyperbolic manifolds, but they're quite difficult. So for the moment then, so for the rest of today, let me stick on, until further notice then, M is going to be so M will be a prime Seifert-Fibert space. And remember we decided yesterday, or maybe before, that the only interesting sort of class of manifolds to look at from the point of view of this conjecture are the rational homology spheres. So a rational homology sphere, Seifert-Fibert space, prime is actually no big deal. Almost all Seifert-Fibert spaces are prime. The only non-prime one is RP3 connected sum. RP3. So there's an exercise for you. If you haven't seen Seifert-Fibert spaces before, why don't you show that this manifold has such a structure? It's sort of interesting. Okay, so let me just make some comments about the conjecture in this context. Okay, so one thing you can do with a Seifert-Fibert space is if you identify each fiber to a point, you get a quotient map. And this is clearly a surface. F will be a, well, here I'm now looking at a closed manifold. So F will be a closed surface. So in the early days, people studied incompressible surfaces in three manifolds, Haken manifolds. And so one thing that Waldhausen proved was that if you have an incompressible surface in a Seifert-Fibert space, then you can isotope it so that either it's transverse to the Seifert fibers, so-called horizontal, or it's just a union of Seifert fibers, i.e. vertical. And of course, the union of Seifert fibers, they're just going to be tori if they're orientable. I guess you can have Klein bottles as well. But so then people looked at the same sort of idea for foliations. And in particular then you have the notion of a horizontal foliation. So let's just say that, so a foliation F on the Seifert fiber space guy we're talking about is said to be horizontal if the leads are transverse, everywhere transverse to the fibers. So the first thing you notice is that horizontal implies taut, because every leaf is going to be met somewhere by some fiber meeting it transversely. And what about the co-orientability? Well, it'll be co-orientable if and only if this so-called base surface here is orientable. Because you can take the fibers, you can use the Seifert fibers to define a co-orientation, and if you get into trouble, that means that you've gone around some loop, and you come back and you're now upside down, which means that you've got a Klein bottle, you've got a vertical Klein bottle in your Seifert fiber space. And of course, all our manifolds M are orientable, so that means that F would have to be non-orientable. Okay, so the first statement about these things, which is not so hard to prove, and I won't prove it. Oh, by the way, this is a good commercial break. I recommend this book, Ordered Groups and Topology by Clay and Rolfson. It's just been published by the MS, and it says almost all the things that I've said and much more. And it's a very good book. So yeah. So the first thing is that. So let me remind you here that remember when we talked about foliations. One thing we could do is we could go to the universal covering and look at the leaf space of the induced foliation in the universal covering, and if that was the real line, then we said that the foliation was R covered, and that was great because then that means that the fundamental group of the manifold, the action on the universal cover will induce an action on this leaf space, and if that's the real line, then we get a non-trivial representation of the fundamental group into homeo plus R. And so by the Boyer-Rolfson-Weiss theorem, that means that pi 1 of m has a non-trivial left orderable quotient, and so pi 1 of m is left orderable. So that was good. And so here, this is good because, in fact, the horizontal foliation is R covered. So, I mean, the point is that the universal cover of, you've got this, well, the universal cover will be R3, and the Seifert fibration, the Seifert fibers, I mean, they're going to induce up in the, they're going to lift to these infinite cylinders, and so they're going to induce a structure of a line bundle, an R bundle over R2, and the foliation is going to lift to guys that are transverse to those vertical copies of R, and so you can show that in fact the foliation is just a product foliation on R3, and so the leaf space is just going to be R. So okay, let's immediately now prove one direction of this conjecture. So, right. Okay, so again, quick sketch here. You've got this Seifert fiber space. It has a coordinable taut foliation. So now again, people generalize this theorem of Wallhausen about incompressible surfaces to foliations. And you can make foliations, well, either horizontal or vertical. But you see, any vertical leaf of a foliation would have to be some torus, and so. But you see, let's put it this way: but because M is a rational homology sphere, and because the foliation is taut, right? Then M has no. It can't have any compact leaves. Because any compact leaf, because it's a rational, we're talking about a rational homology sphere, would have to separate, right? And so now you can't have a co-orientation, right? And so therefore, it turns out, therefore, it's a theorem of Brittenham and Klaus, that therefore you can isotope F to be horizontal. So that. And so now you've got a, and so therefore, so now the result, therefore it's R covered, and so we get, so now lemma 3.1 plus theorem 2.6 gives the result. You don't have to order them. So that's very nice. So in one direction, you always have this for Seifert fiber spaces by fairly elementary argument. We want to prove the converse. So that requires a little bit more work. So at this point, let me say something about the fundamental groups of three manifolds, of Seifert fiber spaces. First, notice that this quotient map, where you identify each Seifert fiber to a point, and you get this surface, the so-called orbit surface or base surface. This map is onto, and so because we're assuming that M is a rational homology sphere, this is a closed surface. It better not have any. It better have finite first homology. So therefore, there's only two possibilities, right? It's either the two-sphere or the projective plane, right? So let's call this case A and this case B. By the way, I mean, again, if you haven't seen these things before, I mean, this orbit surface F can be non-orientable even if the total manifold M is orientable. It's just that you're going to get, you know, the bundle is going to be a twisted sort of bundle. Well, what you can do, let me just say something about, one can then figure out what the fundamental groups look like. And the way you can do this, you see, when you, I mean, you can do this in general, but let's just stick to these two cases. Away from the exceptional fibers, there's going to be a finite number of exceptional fibers. Away from those, you just have a circle bundle. And so what you should do, there may be no exceptional fibers, so really what you should do is drill out neighborhoods of all the exceptional fibers plus one more. Drill out, and so now you get a compact surface with boundary, and over that you just have a circle bundle. So you just have a product bundle. Or if it's non-orientable, I guess it's going to be a twisted bundle. You're going to be twisting as you go around orientation reversing loops. And now, so that's a canonical gadget. Now you glue in the solid tori you removed, and you can figure out what's sort of going on there, and you can write down the fundamental group. And so let me just say what you get in these cases. The corresponding groups here are, well, you get generators corresponding to the exceptional fibers. They really correspond to the boundary components of the base that when you drill out neighborhoods of the exceptional fibers, you're going to left with corresponding boundary component. You're going to be drilling out disks in the in F, so you get a bunch of generators there. Then you get the fiber, the circle fiber generator, and then when you glue back the neighborhoods of the exceptional fibers, well, first of all, you get that H commutes with all these guys, because this is just a trivial bundle. And then when you glue back the neighborhoods of the exceptional fibers, you get relations like this. This is the multiplicity of the fiber, and Ri is something which is relatively prime to Pi again. It's not quite the Q that we talked about. It's like the inverse of Q. But you get that. And then finally, we had this extra neighborhood we drilled out just to make sure that maybe there were no exceptional fibers. And so there, when you glue that back, you just get that the product of all the CIs is some power of H, traditionally called B. If there aren't any exceptional fibers, then B is just the Euler number of the Euler number of the circle bundle. Okay, so that's that. In case B, now you have this base surface RP2, so now it's Z2, so you get an extra generator coming from that. And again, you're going to get generators coming from the punctures in F, if you like, or the the singular fibers. Well, now H commutes with the C's. But of course, the loop A is orientation reversing, and so because the manifold M is orientable, it must be that when you translate H around A, you actually get H inverse. And again, you glue in the solid tori, you get relations like this, and now that extra boundary component gives rise to the relation A squared pi Ci is H to the B. Okay, so that's, I hope you see that that's something you can sort of figure out. So let's look at those. There are two cases then, depending on whether the base is the sphere or the projective plane. Let's first look at the case where it's a projective plane, because there it turns out that there's a kind of uniform answer to what's going on in terms of these properties.
Depend on the order of the CIs?
I'm sorry?
If you're taking the product of all the CIs, does that technically depend on the order?
Oops, what have I done? It depends on the order. Well, yeah, I mean, yes, you have to have a, yes, sure. Right.
There's a stick over to the
There's a stick? Oh, there's a... This is it, is it? Oh, fantastic. Great. Thank you. Yeah. Yeah, I mean, this is the familiar boundary of a, of a punctured surface. That's right. Yeah. And so let's look at the case B first, because there it turns out that there's a kind of uniform, like I said, there's a uniform answer. And let me just say something about this. So, right. So a couple of theorems. The first one is that, so in case B, the fundamental group M is not left orderable. And therefore, by the way, therefore it's not CTF, right? Because so it's not left orderable, and so what about the length space? Well, if it's not left orderable, I guess it should be an L space, right? So, in fact, it is. So this was actually proved in this paper I refer to with Steve Boyer and Liam Watson, that M is an L space. So in case B, these things are equivalent, but they I mean, you just get one possibility. So let me just quickly sketch the proofs of these things. So we've got our group here. So suppose we have let's suppose this is a left order on pi 1 of M. Now you can always reverse an order, right? You can just flip things around, and so without loss of generality, we may suppose then that H is greater than, well, okay, I mean, you can prove that H isn't 1, but maybe it is, you don't know. Okay, we can assume that H is greater than equal to 1. Notice that A is definitely not trivial because it projects to the generator of pi 1 of the projective plane. So let's suppose that A is greater than 1. Well, there's something that I should say here that, okay, when you, remember I talked about removing the neighborhoods of the exceptional fibers and removing neighborhoods of an ordinary fiber and so on. So at this point, you just have this circle bundle over the surface. Now, you can choose annuli connecting distinct boundary components. You can Dane twist about these annuli, and that sort of changes. I mean, really, you're talking about a section. It changes the section, and so the point is that it's not clear from this, but the B's and the RI's. I mean, you can change them provided you keep a certain sum invariant. So just by applying these sort of Dane twists or changing this section of this bundle over the punctured surface, you can. So I want to make Ri positive. So let me just say that by possibly changing B, we may assume that all the Ri's are positive. Okay, now, so what do we do here? Well, look at the relation Ci to the Pi is H to the Ri. The Ri's are positive, and H is at least 1. So this is greater than or equal to 1. Well, that means that Ci is greater than or equal to 1. If Ci were less than 1, then any positive power of it would be less than 1. And so therefore the product of the Ci's is greater than or equal to 1. And therefore H to the B, well, it's A squared times the product of the Ci's. The product of the Ci's is greater than or equal to 1. And so by left invariance, this is greater than or equal to A squared. But A is positive, so this is greater than A. Now, you haven't done your homework, have you? But if you had, you would find that this is a contradiction. So there's an exercise on the homework that if you have a relation, it's very easy, but if you have a relation like this, if A is greater than 1, then H to any power is actually less than A. So this contradicts that exercise. So anyway, the point is, this contradicting exercise 7. So this is, that's just the point is it's an elementary thing. And of course, if A is less than 1, same thing, like you just I don't know, make all the Ri's negative or something. So okay, so this is just an elementary sort of calculation. So it's not left orderable. What about the proof of theorem 3.4? Proving that these guys are L spaces. Well, there we just the number of exceptional fibers n. If n is at most, if there's at most one exceptional fiber, then it's easy to see that pi 1 of m is finite, and so we're okay. And so what we do now is use the exact triad that Adam was referring to today. So now we induct on, and you induct on n. I won't go into the details, but you now just induct on a number of fibers. You do surgery. You do surgeries on an exceptional fiber, and use this. Well, x alpha, x beta, x alpha plus beta. If the first homology of this is the sum of the first, these are Dane fillings on x, and so if these are L spaces, then this implies that this is an L space. So anyway, that's how one can do that, using the fact that you can do surgery so that that these two guys have fewer singular fibers and fewer exceptional fibers. So there we are. So case B, it's fine. All these things are equivalent, and in fact, you're an L space and you're not left over. You're not coordinate. What about case A? Now, case A gets more interesting when you have a sphere. Because sometimes you're left orthogonal, sometimes you aren't. But So let me say something like that. Okay, so we're now looking at case A, where the base is a sphere. So this is the theorem there, and this is due to Boyer, Rolfson, and Least, that in case A, remember, if you CTF your LO, that's a general statement, but the converse is true as well. So let me give a sketch of the proof. I don't know why they're all sketches, right? But maybe this is particularly sketchy. All right. So there's our group. If n is less equal, if there are at most two singular fibers, then it's easy to see that M is a lens space. So we're happy there. It's not left orderable, and it doesn't have a coordinate total foliation, then that's fine. So let's assume that well, okay. Let me just say, for simplicity, just for the sake of writing something down, and it's only for simplicity. I mean, let's assume that n is equal to 3. If n is greater than 3, then you just have to quotient out by some more stuff. But assume that n is 3, and again, let's assume that the sum of the reciprocals of the pi's, p1, 2, 3. Let's assume this is less than 1. If it's greater than 1, you see, then in fact pi1 of m is finite, and we're happy. We're happy there. We know that you are an L space, and you can't be any of the other two things. So let's just, for simplicity, assume we're in this case. So what happens? Okay, maybe let me leave this group up at least. So then we go to the hyperbolic plane, and notice that there's a triangle. So this is familiar, I know, to most of you. So, and then we can now look at the group of isometries of hypermorphism generated by rotations. So if you let gamma I be a rotation about xi through an angle 2 pi over pi, and okay, so now you get a homomorphism. Let me put all this together. You get a homomorphism from pi1 of m. So there's pi1 of m. That's up there, case A. Now you just the subgroup generated by H, the cyclic subgroup generated by H, is central, right? So you can just kill that central subgroup. And of course, what you get is a group with presentation C1, C2, C3. Ci to the pi is 1, and the product of the Ci's is 1. Well, this is satisfied by the gammas. And so you can map this by sending Ci to gamma I to the group generated by gamma 1 and gamma 2 and gamma 3, and let me, for future reference, call that gamma P1, P2, P3, and this is a subgroup of the orientation preserving isometries of the hyperbolic plane. In fact, one can show that this is an isomorphism, that this is precisely a presentation of this so-called triangle group. So anyway, the point is you get a representation, call it rho 1, from pi 1 of m to the orientation preserving isometers of H2. Okay, so that's one thing you can do. That's just from the structure of the Seifert fiber space. Now, we're trying to prove this theorem. So we also know that pi 1 of m is left orderable. That's our hypothesis here. And so, so pi 1 of m is left orderable. And so remember, that implies actually that that pi 1 of m has a faithful representation into homeo plus r. Okay, and you can arrange that so that. I mean, I'm going. Okay, anyway, we can assume that this cyclic subgroup that we factored out by that this acts freely and properly discontinuously on R. And so now you can. So now we have. We have, I guess, let me call this rho 2. So now we have these two representations, and you can put them together to take a diagonal action. And so rho 1 and rho 2 give a free, properly discontinuous action of pi 1 of m, just diagonally on R cross H2. And so this is a covering space action. And so the quotient is going to be some closed 3 manifold. And of course, its fundamental group is going to be isomorphic to that of M. Well, and therefore, in fact, and it's homeomorphic to N. And so now the point is that you get this, these R, the R factors sort of descend to the Seifert fibers of a Seifert fibration of M, and the points across these hyperbolic planes, they descend to a horizontal, the leaves of a horizontal foliation. So that's a quick sketch of that, and so and of course horizontal foliations are well, here obviously it's co-orientable because we have the base Satoussier and they're torn. So that's a sketch of that direction of that proof. Now. Finally, what about the L-space case? Well, let me not say anything about that other than just state the result. Okay, so yeah, let me put. Because I do want to say a little bit more about some other things. So let me just. So in fact, there's a theorem of 3.6 of Liska and Stipschitz that says that, again, in case A, that we're talking about here, if you do not have a co-orientable taut foliation, then you're an L space. Let's put it that way. So case A, no CTF implies L space. Now this proof actually goes via contact structures, which is sort of interesting. But putting all these things together, let me remind you, in case B, you're always an L space and you're never anything else. In case A, well, all three things are equivalent. So the conjecture is true. So summarizing, the conjecture is true for Seifert fiber spaces. And on the other hand, case A, as I was alluding to, I remember if you remember at maybe the first lecture or the second lecture, I wrote up two fundamental groups of three manifolds, and I said, well, one of them is left ordered and the other isn't. And in fact, they were both Seifert fiber space. In fact, they were both certain surgeries on the trefoil that you can figure out which ones they were. And so, so again, there's no uniform answer. Sometimes in case A, sometimes you are left orderable, and therefore all the others, and sometimes you're not. And exactly when it has to be completely worked out. Let me not give the details, but in case A, it's known exactly when. Well, let's focus on the foliation part because that was the way it was proved. Exactly when, and this is old work of Eisenbud, Hirsch, Neumann, Jenkins, Naimi. So again, it sometimes happens, sometimes doesn't, and you can figure out just from the arithmetic data, you know, of the Seifert fibering when it happens. Let me finish by saying something about a special case of integral homology spheres. Keep on losing the.
You should probably remark that Liska and Stipchitz used that result.
I'm sorry?
That Liska and Stipchitz used the classification of.
Yes, exactly. No, they did. You're absolutely right. Yes, exactly. Yeah, they did. Yeah, that's right. Yes. Let me just say a couple of words about, again, for the moment, just again, a Seifert fiber space. Let's assume it's an integral homology sphere, i.e., not only is H1 of M finite, but it's actually zero. And so there, it turns out that, well, obviously, the base surface here, right, must have no homology, so it must be the two-sphere. So F must be the two-sphere. And you can easily see, well, I guess I've erased the presentation, but you can easily see that the integers P1 through Pn will have to be pairwise co-prime. So P1 through Pn have to be pairwise co-prime. And in fact, given such a set, in fact, there exists, right, so given such, there exists exactly one, you know, SFS, VHS corresponding to those things. And again, pi 1 of m, it's easy to prove that pi 1 of m is infinite, except in two very special cases, unless m is S3, or the famous sigma 235 that we heard about this morning, the Poincare homology sphere. That corresponds precisely to 235. Yeah, okay, there's a unique homology sphere. And so here's the theorem. The theorem here is that, so M, a Seifert fibered space, Z homology sphere, then in fact M is LO. So remember, all these things are equivalent, but it's LO if and only if pi 1 of M is infinite. So it's left orderable and therefore not an L space and therefore has a CTF. But if and only if, and of course it obviously has to be infinite. So let me just quickly sketch the proof of that, and then basically quit. But well, we want to prove that we're left orderable. So we want to. So again, as we did earlier, sort of. I mean, you get a homomorphism from pi 1 of m. First kill this. And now you get, well, I mean, I guess n might be greater than or equal to 3. but might be greater than 3. But you can always just project again to some gamma, let's say P1, P2, P3, where this is sitting in the orientation preserving assemblies of H2. You may just be killing some of the other CIs, but that's fine. Now the orientation preserving assemblies of hyperbolic plane, this is isomorphic to PSL2R. If you think of sort of Möbius transformation, real Möbius transformations on the upper half plane, for example. Now in PSL2R, of course, that acts on RP1 orientation preservingly. So you get this representation. Now, this is quite good, but we want homeo plus R, right? Because we want this to be left orbital. Well, there's a universal covering, right? PSL2R tilde, which of course acts on the universal covering of S1. So this is sitting in homeo plus R. So you get this representation here, and we'd like to lift it here. Well, this is a well-known problem. I mean, this is a central extension of this by Z, and so the obstruction to the existence of rho tilde belongs to H upper 2, the second cohomology of the group, with coefficients in Z. But M is a prime 3 manifold with infinite fundamental group. It's irreducible, actually, with infinite fundamental group. And therefore, it's a K pi 1, and so this is isomorphic to H upper 2 of the manifold. And of course, by duality, this is H lower 1, and this is 0 by assumption. And so we get this representation into homeo plus R, and so we're happy. So we're left orbital. If you just give me a couple of minutes, let me finally then say, so that here we are, we've proved that if you have an integral homology sphere that is a Seifert fiber space and is not one of the two finite fundamental group guys, then it's left orbital. So what about arbitrary integral homology spheres? So let me just finish with that as a kind of interesting case of this conjecture. So now M an arbitrary ZHS prime, of course. And so here's the question, you know, is well, is it LO? Is it CTF? With infinite fundamental group. And again, that means, you know, not S3 or sigma 235. By the way, it is known that in this context that CTF does imply left orbital, and it's essentially it's this argument here, except how do you get the representation into homeo plus S1? Here we got it in this very nice way by the group was so nice, we got this quotient which was a triangle group and so on. In general, though, there's this Thurston's universal circle construction. It shows you that if you're a CTF, then you get you get a non-trivial representation of pi 1 of M into homeo plus S1. So this is a story which I won't go into, but you get a non-trivial. And now, again, you want to lift it to homeo plus R, but the obstruction of that is in this second cohomology. And so if you're a Z homology sphere, then you're okay, you can lift. So ZHS. But in general, my understanding is that apart from this implication, these questions are wide open. I mean, presumably the answer is yes to all of them. I mean, none of them are L spaces, but that's for you guys to do. Okay, thank you.
So there's a picture now.
Yep.